So this is lesson 5.2. In this, we will review the effect of influential observations and outliers over the results of the regression model. Note that the content of some slides is not included in the syllabus. I will explain them anyhow because they refer to techniques that are implemented in Gretel, so you will need to understand at least what these techniques are doing to properly interpret the outputs. This is the index for this lesson. First, we will define the concept of outlier and then the concept of influential observations. These concepts are similar, but they are not exactly the same. As you will see, all the influential observations are typically outlying, but not all the outliers must be influential observations. Third, we will describe some techniques to detect outlying and influential observations. And last, we will provide a summary of the main ideas in this lesson. In this slide, we define the concept of outlier or outlying observation. To this end, we will use the dataset Outliers and Influential Observations GDT that you can download from the virtual campus. An outlier, which is also called anomalous or typical observation, is a data point which is so far from the others that we could think that it could be due to a recording error, an exceptional value, or that it comes from a different distributions. Observations can be atypical with respect to the y-axis. For example, consider A and B. A and B are very far from the typical range of value for y, which goes from -5 to, let's say, 11 or 12. A is very large in comparison with the rest of the sample, and B not so much, but also far from the rest of the values. On the other hand, C is atypical not only with respect to the y-axis, but also with respect to the x-axis. This is the model that has been simulated in this case. As you can see, the constant term value is 2, the slope is 1.5. So, which are the effects of outliers over the sample? In this regression model, you are regressing influence 1 over x. So this corresponds exactly to the same example that we have just reviewed. As you see, the coefficient and the slope are very close to the simulated value. 2.14 is very close to 2.0 and 1.54 is very close to 1.50. So an outlier may affect the estimates for the parameters, in this case it is called influential, or may have no effect at all. However, in most cases, the outliers create an appearance of non-normality and heteroscedasticity. For example, if you compute the histogram, sample histogram for the residuals, you will see that most of the residuals are very close to the center, but there are large residuals corresponding to the points A and B, which are far from the regression line and then produce large residuals. So a formal test for residual normality, such as the one that we have here, would reject the null hypothesis. An influential observation is an outlier that has a strong effect over the estimates for the parameters. In the figure, we see that some outliers have large residuals. This is the case of A and B, while others have relatively small ones, which is the case of C. Also, there are some data points, A and B, that have an important effect over the estimates, and in this case we call them influential. For example, if we imagine that A is deleted from the sample, then we would expect the regression line to move upwards. However, if we delete B while keeping A and C, we will expect the regression line to move downwards. An outlier may be also non-influential. This is the case of C. If we delete C from the sample, the regression line would stay more or less in the same place. The problem of influence is very subtle, as the condition of influential non-influential value of an outlier may depend on the presence of other observations in the sample. This slide illustrates previous ideas. In the first figure, we show the result of regressing X over base data. In this case, the dataset has no influential values or outliers. As you can see, the regression results are very close to the true values, and the test for residual normality does not reject the null. The coefficients are similar, on the other hand, to those computed with the three outliers in the sample, A, B, and C. And this means that A, B, and C were atypical values, outlying values, but they were not jointly influential. In the second figure, we see the regression of X, the X variable, over influence 4, which is the data set after deleting points A and C and keeping B in the sample. In this case, the model parameters are substantially influenced by the presence of B, and the test for normality strongly rejects the null. Therefore, and this is the main idea that we need to retain, an observation may be outlying or not by itself, but its influence will depend on the presence of other observations in the sample. Now let's talk about the tools that we have to detect outlying and influential observations. The first tool is very simple. It is just the histogram for all the variables in the model. The first figure, this one, has the variable x, that is the regressor in this axis. And here you have the density, the sample density, and in comparison the density for a normal variable. In this case, we see clearly that there is one value in the tail of the distribution, this one. This value corresponds to the point C, which is therefore outlying with respect to the x variable, the x-axis, because it is far from the center. In the figure below, we have the histogram for influence 1. Influence 1 is the sample for the values of y that has the data points A, B, and C. As you see, you have large values far from the center, in this case, over 0, and also values under 0. This would correspond to B, and this to A and C. So outliers are always in the tails of the histogram, but not all the observations in the tails must be outlying. This is a criterion to separate outliers with not outliers. First of all, bear in mind that a normal or a t-distribution has 5% of its values in this range of plus minus 2 standard deviations. So you could expect, under normality or the t-distribution, to have at least 5% observations over 2 sigmas or and under 2 sigmas. It is very difficult, but not so rare at the end of the day, to observe values between the mean plus minus 3 sigmas, and it is close to impossible for a normal distribution to yield a value deviating more than 4 standard deviations from the mean. So this is a criterion to classify an observation as outlying. Now let's talk about the tool which is useful to detect outliers with respect to the x-axis. This tool is called the coefficient of leverage. The coefficients of leverage are the values in the main diagonal of this matrix, which is called the hat matrix, H. They are a scale-free measure of the size of each observation of x, and so it is useful to detect outliers with respect to the x-axis. To see that this is measuring the size of x, note that we have something here which is a vector version of a ratio. In the numerator of this ratio, we will have x times x transpose, so something that we can assimilate with x squared. And x squared is divided by something that is the inverse, in the center of this expression, of x transpose x. So as we multiply and divide numbers of the same scale, this is the reason why we get a scale-free measure. And this is measuring the size of x squared, actually, which is in the numerator. This matrix is known as the hat matrix because H transforms the observed values y into y hat. To see this, note that y hat is computed as x times beta hat, so x times this expression, and the matrix that we have here multiplying y is actually H, the same H that we defined above. So this matrix H puts a hat over Y. So this is the hat matrix. Bearing in mind this definition, the ITF coefficient of leverage will be defined as this. We can compute it in this way, and it would measure the effect of xy over y hat given the value of y hat. It can be proved that the coefficients of leverage are bounded between 0 and 1, and the sum is equal to k, the number of regressors. So the average is k divided by n. Therefore, a coefficient much larger than k divided by n points to an outlying x value, which may also be influential because it has a large effect on y hat. Now we will consider another tool which is useful to detect outlying observations with respect to the y-axis and also to test for the influence of this observation. This is called the Kook Statistic. The Kook Statistic tests two things. Basically, the difference between the estimates calculated with the whole sample and the estimates for beta calculated eliminating the ITF observation, or equivalently, the difference between the expected value of the endogenous variable and the same value computed excluding the ITF observation. The first interpretation is formalized in this expression. Here we have the Kook statistic, denoted by d sub I, is equal to the difference between beta hat computed with the whole sample and beta hat parenthesis I, which is computed without the ITF observation. The expression of the Kook statistic is this one, and this expression tests the null that beta hat is equal to beta hat subtracting the ITF observation in the sample. Under this null hypothesis, if the null hypothesis is this, under this hypothesis, the Kook statistic has this distribution, where k stands for the number of parameters in the regression, and n minus k is the number of degrees of freedom. The second interpretation is formalized in the second alternative expression, which is mathematically equivalent to the previous one. They both yield the same result. So the Kook influence statistic can also be computed as y hat minus y hat subtracting the ITF observation in the sample. The sum of square of these values divided by k times the estimate for the variance of the error has also the same distribution and is testing the null that y hat is equal to y hat parenthesis y. Next, we will review a simple tool to detect outlying values with respect to the y-axis. This tool is called the Studentized Residual. Note that this slide will not be evaluated in the exam, but Gretel computes studentized residuals, so we want you to be able to interpret these results. Imagine that you have here the regression model that you want to estimate, yt as a function of xt transpose. And then you add a new variable with its corresponding parameter. The variable d is defined as 1 for the ITF observation and 0 otherwise. So, for most of the sample, d sub t super yi will be equal to 0, so this value here will not appear in the sample. However, when you get to the ITF observation, the variable d will have the value 1, so you will correct the level of the model by this amount. You are allowing for a level change rt equal y. Under this condition, we can test the null that y sub I is not outlying by testing the null that delta sub I is equal to 0 with a standard t statistic. This t statistic can be computed in this alternative form. This is called the studentized residual. Here you have the residual superstar, which is studentized. This is the standard residual. This is the unbiased estimate for the standard deviation of the errors. And you have here the square root of 1 minus the leverage coefficient for the ITF observation. The same leverage coefficient that we defined a couple of slides ago. Under the null that delta is equal to 0, the distribution for this residual is a t with n minus k minus 1 observation. So this is a easy to compute statistic building on the result of the standard regression model. There are two other statistics that Gretel provide and that will not be evaluated in the exams. These are called the influence and the DF-fits statistic. The influence statistic is the difference between y sub I hat minus y sub I hat computed without the ITF observation. This is computed in this way, where h is again the leverage coefficient, and this is the residual, the standard residual of the regression, considering all the data points in the sample. Therefore, you are testing for the influence of the ITF observation over y hat. Second, bearing in mind that the variance of y hat is equal to this value, the DF-fits statistic is computed in this way. So again, it is testing for the difference in value of y hat and y hat computed without the ITF observation. This is therefore useful to detect outlying values with respect to the y-axis and can be interpreted in these both ways, as a scale-free measure of the distance between the fitted values and as a scale-free residual. This slide, which again will not be evaluated in the exams, is devoted to explain how Gretel implements the detection of atypical and influential observations. When applied to the standard case that we are using time and time again in this lesson, we have 25 observations. We have the residual for each data point. We have here the leverage coefficient with a star in this case. We have an influence measure here and the DF-fits coefficient here. And this is the display, a display of this statistic. As you see, when you get to this observation, number 23 in the sample, the leverage coefficient jumps up. So this observation, which corresponds to point C in the sample, is an observation which is outlying with respect to the x-axis. On the other hand, the influence statistic is pretty large for the 23 observation, but very, very large for the 24th and 25. So these three observations are potentially influential. This is C, and these are A and B. And these are finally the highlights from this lesson. You just need to read them. This is a summary. They add nothing new over what we have just explained. So guys, I hope that you have found this presentation useful. If you need further clarification, you can use this email address. I only use it to teach this econometrics course. And if required, we can also have a chat through Skype. My nick is Jerezmik. You can find me here. So that's all. Good night and good luck.